Okay, we'll come on that later on. See, we will continue on irregular wave motions in irregular waves. Okay, we will continue the discussion on that. At the very beginning, now I want to tell you about this unit, just for checking, because it's always a good diagnostic. See, we have got this omega e and say response. What is SR omega e? This is given by S E omega e into H omega e square. Okay, this is the formula. What is this unit? This is meter square second. Now this unit you will be coming now H omega. What is H omega e? This is actually the amplitude of the response divided by the amplitude of the wave. So it is response amplitude by wave amplitude. So this is going to be meter by meter for heave, roll and pitch, or it's going to be say degree by meter for the angular motions. It is going to be this for linear motions, this for angular motions. All right, because it is response by wave. Now, if supposing it is meter by meter, then this becomes meter square second into meter square by meter square. So this becomes meter by. So I will just write it again here, because this pages, the problem is that SR omega e equal to S E omega e into H square omega e. So this is meter square second into meter square by meter square gives you meter square second. Okay, this is for linear motions, or this is meter square second into degree square by meter square give you meter square degree for angular motions. Okay, that is what it is. Now area under the graph is going to be this into omega e. So m0 unit is meter square degree into there is a second there, sorry, for first one. I made a mistake here. Meter square second, no, this is meter square second into degree square by meter square. See, it is meter square second into degree square by meter square, that is going to be, sorry, I am working degree square into second. This is what it is. Yes. This is meter square second multiplied by 1 by second. This is meter square for linear motions. For angular motions, this is degree square into second into 1 by second, that is degree square. So root over of m0 will be meter, root over of this will be a degree, simple as that. Actually it is more simple to see that, because this is response amplitude unit square divided by, see in a more general way it is something like that. This equal to S E omega e into H R square omega e. This is actually unit of meter square second. This is into the unit of response square by meter square. If this gets cut, so this becomes actually unit of response square into second. So the integration becomes multiplied by 1 by a second. So m0 becomes unit of response square. So m0 therefore root m0 has a unit of response. So that is why the area under the response curve always have a unit of response. So when you took m0, it will have a unit of response, but if you take m1, it will have a unit of response into omega. So response into 1 by second. If you take m2, it will be response into 1 by second square. Okay, if you take that. Now there is a very interesting thing with respect to those and velocity, etc., that I want to say about that part. The next part, before I can go to this velocity. Now you see, we will take a simple case of wave only. Now a wave was, eta was given as an amplitude into cos omega t, let us say EET plus something, kx plus some beta or something. So eta dot is velocity. This is going to be omega e, a omega e into say minus sine of this thing, and eta double dot equal to minus omega e square a omega e cos whatever. Now the point is that amplitude of wave is a, amplitude of velocity is omega e into a, amplitude of acceleration is omega e square into a. Okay, that everybody knows, that you just have to multiply with that. This is for wave. Now if you take now if you take this instead of eta, if you take it as a response, say heave. Heave is also an amplitude into cos omega et. What is heave velocity? Omega into amplitude into sine of this thing. So let me take a response. You take a response. Say heave. So Z t is given by amplitude, of course at a given frequency, into cos omega e t plus something. This is my heave amplitude. Yeah, amplitude of heave response. Okay, everybody understand that. What is my Z dot t? Is going to be omega e z a omega e into sine of something. This is, what is this? This is my amplitude of velocity response, heave velocity. This is amplitude of okay. Now what is z dot dot t? This is going to be minus, forget the minus part, omega e square z a into say cos of something. So this becomes my amplitude of heave acceleration. What I am trying to say is that, now this is very important, whenever you have a sinusoidal motion, see if there is a displacement amplitude of some amount, then velocity amplitude becomes omega times that amount and acceleration becomes omega square times that amount. So the amplitudes of velocity and acceleration are simply multiplied by omega e. Okay, so the response amplitude of velocity is omega e times displacement amplitude, like that. All right. Now comes an important question. Therefore, I can write it like that. Say heave velocity displacement amplitude is Z A. Heave velocity amplitude is omega E Z A, and heave acceleration amplitude is omega E square. Let me call this to be heave velocity instead of this thing. So say heave velocity amplitude. I am calling ZAV to be heave velocity amplitude, okay, and I am calling say Z acceleration amplitude, like that. See, ZA omega E is displacement amplitude, ZAV omega E is velocity amplitude, ZA omega E is acceleration amplitude. This is equal to this, this is equal to this. What is RAO for displacement? That is given by ZA by A, wave amplitude, right? What is RAO for velocity? This is ZA, the V e omega E by A, which is nothing but omega E times ZA omega e by a. See ZA v, that velocity amplitude by wave amplitude, is RAO for velocity. Remember that RAO means always what is the amplitude of response per unit wave amplitude. The two units need not match, isn't it? Because I have got what is the unit of roll in degree per meter of wave height, for example. What is my amplitude of velocity per unit of wave amplitude? ZAV, amplitude of velocity divided by amplitude of wave. But amplitude of velocity is nothing but omega e times amplitude of displacement. So, it is this. Now, this is of acceleration is ZA acceleration by A. Actually, it is turns out to be Z. You can see I will write in two phase now. This will become omega e times amplitude of velocity divided by A, or omega e square times amplitude of displacement by A. In other words, what happened? The RAO is nothing but amplitude by A. So, the way the RAOs also change, RAO of displacement into omega e gives you RAO of velocity, into another omega e give you RAO of acceleration. See, after all, RAO and displacement is only that you just divide this amplitude by a constant A wave amplitude, you get RAO. Okay, so the way that this change, like this into omega e gives you this into omega e gives you this. Similarly, for RAO also, this into omega e give you RAO for this into omega e gives you RAO for this. So, the RAO, that response amplitude operator for velocity and acceleration, also gets available by multiplying with omega e, as simple as it. All I have done is that, see, the bottom part is same, you are multiplying this. See, velocity is velocity amplitude by A, but velocity amplitude is omega e into ZA omega e by A, the top part. Acceleration is ZA amplitude by omega e, that we can show. In fact, you can get this by differentiating this once. So, I just wrote one, it becomes omega e ZA v by A, or omega e square ZA by A. It is a very simple matter of taking one level higher differentiation, that is all. Why we say that? Because tomorrow I want to find out, say, spectrum for velocity, not spectrum for let us say for displacement. So, now this I will now write this, that it turns out that RAO for acceleration equal to omega e times RAO for velocity equal to omega e square times RAO of displacement, or an RAO of velocity equal to omega e times RAO of displacement. Okay. This is what the standard formula is. Now, let us say how we have done response of something. This is equal to RAO square into SE omega e. This is what we have got. This is my formula, isn't it? That response spectrum is RAO or H. This we have called this to be H omega e in my writing. Same as this.
Instead of RAO W, we write H.
We have written H, but I am here calling RAO because this H will be changing. That so this what I want to say is that now what would happen, that if you take SR omega e for displacement, okay, then you get RAO. Let me not write omega e displacement, this square into SE omega e. Okay. See, if I want to find out what is my displacement response, then that is RAO for displacement square into wave amplitude. Okay, this much we have done always, throughout we have been doing that. But if I want to find out what is my this thing of velocity, then I must take RAO square of velocity into SE. That is what I should do. But RAO square velocity is the square of this, which is omega e square into RAO square displacement. Now, you see RAO square velocity, Now here, now carefully see what is RAO square velocity. This is this. So if you square that, it becomes omega E square into RAO square displacement into AC omega E. But what is this? This is my SR omega E displacement
That means SR omega displacement
into omega E square, as simple as that. That is what I am trying to tell you. So it becomes this into omega E square, simple as that. So this maybe I should write in the next page because it is this thing. So what therefore the interesting part that we have obtained here is that SR omega E velocity turns out to be omega E square into SR omega E displacement. Okay. Now same token, if you see that SR omega E acceleration will be turning out to be RAO for acceleration into SR omega E. This is square, of course, and you will see that this one, if you go back to this, now there are two steps. This one is square of this or square of this. That means this one is omega E square RAO velocity. That means this one can be written two steps, omega E square into RAO velocity into SR omega E. This is like this, or it can be written as omega E4 into RAO displacement square into SR. Why is 4? Because you see, if you square that, omega E4 into RAO square comes in, this part. So now, interestingly, you will see here, this part is, I kept omega E square, this part is nothing but SR omega E velocity. See, RAO square velocity into SR omega is obviously SR omega E velocity, and this part, if you see here, is becomes omega E4, of course, here into SR omega E, see, displacement. So what you are now, I will summarize. What you get is that, see, velocity response is omega E square displacement response. Acceleration response is omega E square velocity response is equal to omega E4 displacement response. So it is simply multiplying by a square of the amplitude, that is all. Okay, this is a very interesting phenomena that we should know, and then we will find out why it is important. I want to tell you this. There is the mathematics is very simple. I'll summarize it in summary. Black one maybe. SR, I am writing this way, acceleration equal to omega E square into SR omega E velocity equal to omega E4 SR omega E displacement. Okay, and SR omega E velocity equal to omega E square SR omega E displacement. So now you have got this SR displacement, say displacement. Take any value here, just replace here this into square of this. Okay, so you get this graph. That means, say this value, say A, say this value is omega E. So here the equivalent value is A into omega E square. You will get here SR omega E velocity, and take here A into omega E4, then you will get SR. So you see, you can get this to this spectrum, just one more step, that is all. All you do is that corresponding value multiplied by, see, you have got omega E, so you have got omega E versus SR. Simply write, this is for displacement SR, velocity will be square of this into this, acceleration is going to be square of this. I will make a table next step, but this is very simple, very simple. Like if you look at this the mathematics part of it. Absolutely straightforward and simple. Okay. So now what we have done is, see that you have got here omega e. Let us say you have got SR omega e. This is for displacement. Then you will write here SR omega e of velocity equal to, if I call it A, if I say A, if I call it B, this is simply A square into B. A square into B. You have got these numbers. So you have got this, and this value is square of this into this. Here you write SR omega is acceleration. This is A4 into B. 4 power, this 4 into this, or you can say square of this into this, which is the same thing. You see, A4B is A square into A square B, same thing, isn't it? That's what we have done before. So you get this. So you are getting at same time acceleration spectrum, velocity spectrum just from the same table. Very simple, absolutely simple. You have got the same table. You just take one more line. If you are doing computer program, you have one more line. You say that SR omega e I equal to A square B. Next one is A4B. That's all. So it is a the concept, the application of it or calculation following this is very simple. All that people get confused is the concept. If you get the concept clear, I tell you in your fingertips, you can give these numbers very, very fast. There is no problem on that. But this is the calculation part of it. What I will now discuss little bit is the practical implication of this velocity and acceleration. But before that, there is a very interesting part with respect to m0, m1, m2. Now you see m0 for displacement is area under the displacement curve, that is SR omega e d omega e. Let me write this as d as displacement. Okay, 0 to infinity. What is m2 of displacement? This is 0 to infinity omega e square SR d omega e d omega e. But this part is nothing but SR v omega e, because SR v omega is omega e square SR d omega e. So this becomes equal to again 0 to infinity SR v omega e. So this is nothing but the second moment of area under the displacement is nothing but area of the velocity spectrum. You get my point. This is very interesting. You see, m2 of displacement is omega e square SR displacement of d omega e, square of that. But square of that is nothing but velocity. Actually, this is more illustrated when we will draw the spectrum. See, I have got the spectrum here, displacement spectrum, which looks like that. Okay. Now I took this value. Now what I do that I took this value and I plotted here. This is A here. This is here C omega. I plotted here omega e square into A. Like that I plotted this graph. Okay. What is this graph? This graph is SR omega e velocity. This graph is SR omega e displacement. So you see, the velocity spectrum is nothing but ordinates are taken square of this. I mean this into square of that. What is that? That is nothing but taking second moment of area for this, because after all, if you now look at that, see this value is nothing but second moment of this about this line, because it is this into square of this. See, when you take this into square of this, see if you take this into square of this, omega e square A is this. It essentially means that this graph is nothing but second moment of area for this graph. Each point is second moment of area. In other words, the area under this, if m0 for velocity is becomes m2 for displacement. Because what we are doing is that, see, after all, when I am taking velocity, all I am doing is replacing the ordinate by ordinate into square of the frequency, but that is nothing but the second moment of that ordinate. So therefore, and that is nothing but m2 for displacement. So m2 for displacement is m0 for velocity, and you will find out similarly m0 for acceleration will be m2 for velocity will be m4 for displacement. I am not going to prove that now because we are probably going to run out of time, but you will find out there is a extremely nice sequence involved here that I will show you in a tabular form, which will be much nicer. You will find out that area under the velocity curve, is equal to second moment of area under the displacement curve. Area under the acceleration curve is second moment of area under velocity curve equal to 4th moment of area under displacement curve. How does it go? In a table form is like this. You are writing here omega e, you are writing here SR omega e for displacement. Okay. Now here you write omega e square SR omega e. If you do that and add that, see, as I said, if I did and add that, I've got m0. If I did and added, I got m2. And if I did m4, I added that, I would have got m4. But remember that this is nothing but SR, this is displacement, velocity omega e, and this is nothing but SR, acceleration omega e. Therefore, what you get m0 is nothing but m4 is nothing but area under the acceleration curve, which is m0 for acceleration curve. What you get under m2 is nothing but area under velocity curve. So you see, it becomes very, very simple thing. So in other words, you don't even have to draw that. You make a table there and you simply find m2, m4, etc. And if you found out that, that becomes acceleration. So you can get the value. Now again, suppose you want to find out what is my significant value of velocity. Obviously, say what is my significant velocity. This is going to be some factor, say 2 times root over of m0 under velocity curve, which is nothing but 2 times root over of m2 under displacement. Because m2 under m0 under velocity, that is area under velocity graph, is nothing but second moment under displacement curve. Similarly, if you want to have significant acceleration, it is 2 times of m0 under acceleration, it is 2 times of m2 under velocity, is 2 times of m4 under displacement. So you can get one to other very quickly. There is no problem at all. It is very simple and very straightforward, very nice. There is no problem. This is what I want to tell you, that these acceleration velocities are very simple. Okay, one is nothing but the reason is because in a sinusoidal motion, each of them differ by a frequency. That is the only thing. That is why it becomes so simple. Even it is 1 meter heave, the period is 10 seconds. Then every 10 second 1 meter, so actually 1 meter per 10 second is the amplitude, and 1 meter per 10 second is the acceleration. So that becomes absolutely related. Now comes the question about the relation with the spectral shape. As I mentioned before, this is very interesting. We should see that. Let us say this is omega, and I have got one response spectrum only. Let me say response only over displacement. So it is having a resonance peak here, something like that. Now it is somewhere here. Now you see what would happen if you now try to find out the acceleration, velocity. Velocity is going to be square of this, square of this, square of this. Let us look at the peak value. Peak value is going to be this into square of this. So it is going to be something like, let us say it will go up something like that, and go something like that. This value is going to be this into square of this. Now supposing the graph is not like this, but the graph is like this. Same height, but graph is like this. You take the second one. Now the peak value of that is going to be how much? Again this value into square of this, but the square of this is now much less. So therefore it is going to appear here much less. So you see that what is happening is that if now this is very interesting, because what is happening if now what is this? This is a low frequency, means high, the frequency is low. Okay. So this value has become now, because the frequency is here low here, okay, frequency low means period is high, that means it is happening every so much later. So when the frequency is low, the maximum value of velocity becomes low, even though the displacement is same. In other words, this is interesting because if supposing I have a ship, let us look in terms of period. Okay, let us say this higher one. So let us say this is t equal to say 10 seconds. Obviously, this is going to be lower period, means t equal to say 15 second, I mean higher period because lower frequency. So, supposing I have a ship at t equal to 10 second having displacement of 1 meter per second, 1 meter, then I will have certain amount of velocity, but if the same thing happened at 15 second, I have got a lesser velocity, and if this got shifted, in other words, if this was to get shifted here further, then I would get the amplitude much more. I will show a more I mean extreme diagram. You take a case of this and another case of this shifted. See, the response is shifted. One is behaving at low period, one is behaving at high period. This is going to be actually the case for a small boats. This is going to be for this is going to be small boats. Small boats will be responding at high frequency. I'll mention that later on. But let us say there are two cases there. Now this one and this one, if you look at the acceleration and velocity, the velocity for this one probably, let me draw from here. Maybe it will look something like that, but this one is going to look like that, because here you are taking every value square of the distance. So you see this peak value, this value is this particular value. Let me say call this to be A. This is going to be say omega 2, A into omega 2 square. This is going to be A into omega 1 square, but omega 1 is much less than omega 2, therefore this is much higher than this. So you find that if the ship is responding at higher frequency, then its velocity becomes much higher, acceleration becomes much higher. And obviously this is in conversely, if you see that the moment of this graph about this is lower than moment of this graph about this. If you take the second moment of area for this graph, it is much more than this graph. Second moment of area is nothing but the velocity. So you can find out this. So this is an important part with respect to my response. We will now come to see about the tuning of response a little bit, and how we can see about this this part, the velocity part and all, how this is important. You see, there is a very nice example given here. I will try to draw it as much as possible. Three cases are given. I mean, this is an example to show how the tuning of a ship with respect to a spectrum becomes important. Okay. Now there is a response graph here. It is 0.5 second here. This response does not change. It is something like that. This is there everywhere like this. A container ship. This is my H omega E. See, this is my RAO in here it is of heave. Let us say this is an RAO of heave. Obviously, the ship has got some particular resonant frequency, so it is picking up. This is my resonant frequency, it goes up like that. This is my say this is 0.5, something like that. Okay. Let us say this is what it is. See, the ship response do not change. I am here showing a particular container ship, how it behaves in different sea states. Here we are changing the sea state, but response is same. That means the container ship is moving at certain speed with certain heading, that remains unchanged. It is going at that certain V and certain mu. Okay. All of them are going at that, they are not changing. The V and mu is not changing. All right. When V and mu changes, of course, we will have a difference there. Now there is a spectrum, low, high, etc. So let us say there is a spectrum here which is low sea state. So what happened in this particular case, low sea state spectrum will look something like that. Sea state is low. Remember, this is a lower sea state where the waves are occurring at much higher frequency. Now you see, if you look this into this, because this peak is not matching with that. Now if you take, when it is the largest number of waves are there, very less response is there. When the large response is there, very less waves are there. So this area will become, if you multiply square of this into this, it looks very simple, small. Because where the largest waves are there, that this is not there. Now you take now a C state which where this is shifted, C is grown. So obviously it has shifted this way, so now it has gone something like that here, you know. Now here this is closer to this, so you get slightly more area here. Now you say C state where the C is even larger, so this has become, C state becomes like that. Then here you will find these and these are absolutely matching, so this is going to be very large. So you see here, in this case, because the C state has waves which is those waves where you are not getting the response, you are, when you multiply this with this, you get very small response. In other words, the waves are not tuned to the response. See, the shape is responding at this frequency, which means if there are waves of this length corresponding to this frequency, it would behave badly. But this C state has less of that, so you have got very less. This has got slightly more, this has got most of them. So you can see that you end up getting a very large response if you had the tuning of so called the resonant frequency with the peak frequency of the spectrum. Because peak frequency of spectrum, basic, of course these are all transform frequencies, remember these are all S omega E's, this side, and this is S R omega E, what I am trying to show here is, obviously this is a very interesting and important phenomena about the tuning of wave with this. So you have a shape which, let me give an example that 0.5, I do not know how much length would be, 2 pi by 0.5 is 2 pi by 0.5 maybe 6 by 0.5, 12 second, maybe this is probably equal to a 200 meter long wave. Let us say this is about 200 meter long wave. Lower C state, I have no 200 meter long waves, very less, so it does not matter. Slightly higher, I have got little more waves which are close to 200. Slightly more higher, you have got much more waves close to 200. So you end up getting like that. This is actually what happened to large vessels. You see, large vessels, what happened, the period is somewhere, resonant frequency comes somewhere at this side, because I will discuss that again in another class, next probably class. But let me take that most ships would have in heap period etc. maybe 12 to 14 seconds for large ships. That means it is somewhere here, okay. And in rougher weather you have got more 12 to 14 second waves, so they are getting tuned. So it is becoming like that. Now what happened, suppose, so this is one way of tuning, that is wave with response at a given speed. Now what happens, suppose you are in, let me put it this way, now suppose you are in this one, you are going in this C state and you have got this very large response. You know, this if you take the area under that, maybe that this is very large heave you are getting, okay. What do you do? Now what you do, you cannot change this. What you can do is that, now supposing I now go at slower speed, I cannot actually normally speed up more because speeding up is more difficult. Say I change my heading. Now if you actually, if you remember, if you go at higher speed, okay, when V is more in a head waves, this gets stretched out, okay. In fact, if you go at, I mean if you change the speed, what will happen, if you head into the waves, you are going to actually have this stretched out like that. But here what you do is that, say you go slower speed. If you go slower speed, what would happen? That one, in a 1 minus omega V, if you see the formula, 1 plus omega V by G, V is less, omega to omega is smaller. So this will actually get, there will be some change. This will probably become like that. Now this now may not tune with that. If you do that, then this may actually become, see when this is maximum occurring, this has become less now. It is basically other way around, so this might become smaller. Because what is happening now, the peak value which was matching with this, you are changing. See, earlier what happened, this peak and this peak was matching. That means the 200 meter long waves, encountered waves, were causing the ship to heave very much. You change the speed. Now, as you change the speed, you are not encountering 200 meter long waves anymore, you are encountering some other meter waves, most number. So, you have got detuned. This is what you can do by changing voluntary, basically voluntary speed reduction. When you meet, in many things you can do, say basically what you are doing is you are changing this shape, change S E omega E by changing V and by changing mu. Okay. Therefore, this is not tuning. You cannot change this, remember. This cannot be changed because this is the intrinsic characteristic of the hull. The ship that you design behaves badly in a 150 meter long wave period. So, 100 meter wave is 150 meter long wave, or I could say in a certain frequency. It has a natural period of say 12 seconds, it is 12 seconds. Whenever the excitation is 12 seconds, somebody pushes every 12 seconds, it will go up and down very badly. You have to make sure that the waves that exist do not cause that 12-second tuning. How do? You change the speed, change the angle. And in fact, this is also related. If you have a large speed, actually heave and pitch motion, you end up getting what is called large added resistance, large additional power, and that is where comes the concept of ship weather routing. Sometime you never go from A to B straight line, you might actually change, and you may find out that your fuel consumption is overall less, because if you went from A to B, maybe your motions are so large, you have to maintain speed of 15 knots, you have to burn more fuel, or you are having a less speed, more resistance is there. So, if you go slightly away, you may reach at the same time burning the same fuel. Fuel burning will be same because your RPM is same, engine running at the same speed. So, then supposing your engine is at the same speed, you have to go from A to B. So, you have two options. You see, if the engine is the same speed, your fuel consumption is same. So, you try to find out which is the route where you can reach B at the shortest possible time. Now, it turns out A to B straight line may not be the case. This is where the concept of weather routing, and people actually slightly route, companies are there who will give you this. A very interesting example I will tell you about semi-submersible, etc., why it is evolved, that, or before that a small ship. It turns out that, you see, that we have discussed that natural T natural let me talk about this little bit, because that gives you the tuning factor slightly. Now, this is given by, well, 2 pi divided by say rho g AWP by mass plus added mass, omega root over of that. Okay. See, in other words, omega is this thing, or I can write it this way. This formula of that natural period, see, omega is root over of rho g AWP by m plus ma, and t is 2 pi by omega. So, 2 pi, no, this is the 2 pi is outside, sorry, this 2 pi by root over of this. So, this becomes m plus ma by rho g AWP, I think like that, if you replacing something like that. Okay. This is my T natural period. I mean, I will discuss that afterwards. What I want to say is that, see, we have told, I mentioned this earlier, that if a ship has a large AWP, but not so much large mass, which means the ship is very shallow, like a barge, large beam like a barge, low T, high B, B gives you high AWP. Okay. If that is the case, so this is high here. Okay. This is what would happen to a small barge. All right. See, the one that goes along Ganges, you will find that this becomes low, because this is actually high, so this becomes low. This might become say 6 to 8 seconds. Okay, for a typical barge. For a typical ship, let us say tanker, you will find out that say frigate, for example, where AWP is they are normally deeper, T is more. Then for a say frigate, for a ocean tanker, for example, this may be actually 10 to say 12 seconds, maybe more. But if you look at a semi-submersible, I mentioned that perhaps where AWP is much lower, because that is the idea that you lower the AWP very much, you actually make a semi submersible so that your area is very much lower, but for safety you have to have high ISO, you separate out, that is why they are called column stabilized semi submersible. Anyhow, here we will discuss that, I will discuss the numbers later on, but typically this might be say semi submersible, it may be 20, say 25 second. Okay, let us remember this part, it can be quite high. Now you see how the behavior would be in a large ocean. Now typically I want to show you here that typically there is the spectrum here, wave spectrum here. Now the three cases we are considering. This is a wave. What is this? This will be equivalent to actually something like say 10 to 14 second. Most of the cases the peak will occur at around that period. You know, the omega will be such that peak occurs at that period. Remember that this side is omega, that means this is actually T is this side, higher of that means lower this thing. Now a barge typically would have a response like this, because it's all you know, like something like maybe this is maybe something like this, or maybe something like this, something like that. A barge might have, because you know it has got a higher peak, it is about 6 to 8 second period. This is heave, RAO. So I am talking of heave RAO for a barge. Now for a typical ship, this will come down this side, so it may be something like that. And for a semi submersible, this will be actually much below that, it may be something like that. Now you see, if you multiply this with this, you see here, because this is 1 here, this is all, this is 1, because it's actually, that means that it behaves like a wave. So square of that is quite large, so it is going to actually give you a response. I just draw the response here more or less, because this full part has got large parts. So you see, square of this into this will give you something like a big value. So it will give you some kind of a response curve like that. This one is going to give you actually even higher response probably in this case, but this one is going to give you very low response, because here the values are very small and this is occurring here. So what will happen is going to give something like this. What I am trying to say here is that if you see this interesting part, you will see that in a typical sea state, in fact if the sea state is lower, then it would have been like that. So you see what happened, a lower sea state, I will end it here in soon. The lower sea state, just simple, lower sea state means sea state say 3 or something, okay. When the wind is blowing at 20 knots, you are having more number of waves of 6 to 8 seconds, but that 6 to 8 second waves the barge behaves badly. Therefore, even in a very low sea state, barge behaves very badly. Higher sea state, it obviously it behaves badly because it is 1, that means it simply goes up and down with the wave, okay. Now you take for example a large tanker, lower sea state, it may not respond, because lower sea state, you know, this peak goes on the other side of that where it is coming down. So it may not respond lower sea state. At higher sea state, means say sea state 5 or 6 where the period is 10-14 seconds, it will behave very badly. Still higher, it will behave very badly. So a large tanker, that is why do not respond to small waves, but large waves it will respond. If you take a semi submersible, it is by design, the semi submersible is designed such that its peak is much away from any peak, say 20 second no waves exist except very small. There are simply no waves to cause excitation, so it has very low excitation. Why it is designed for this? See, there is a I will end in a minute. There is a big reason for that. The reason is that ship has the privilege of running away if you encounter bad motion. You can just change. Semi submersible or offshore structure is designed for one place. So if you have a bad weather, you simply have to go up and down. You cannot afford to have bad weather by design of the hull. That is why you have a semi submersible design. This is why semi submersible concept and similar concept has come for SWAT hull, small water plane area twin hull. I will talk about that next class, but this is a very interesting part of a small boat, barge, or you may say a small petrol boat, pilot boat. Everybody says the pilot boat's going to, this thing is not comfortable, pops up and down. Same reason, no large waves, but still pops up and down. But you go in a tanker, small waves doesn't happen. So day to day life you are not bothered. In a tanker you would rather be assigned on a tanker than on a small pilot vessel, and semi-submersible is even better. So anyhow, I will end it here. We will have more to discuss next class on the same topic of now coupled motion, etc. Okay. Thank you very much. I will end here. Okay, today I am going to talk on the first lecture on two topics. One is what I call motion in short crested, basically 3D waves. This I will talk first, and later on maybe what I am calling coupled motions. See, the reason I want to talk about motion in short crested wave is that so far what we talked earlier was a motion in what is called a 2D or long crested waves. Okay. We have briefly discussed earlier how we can describe a short crested wave by simply multiplying this with a spreading function and taking also the fact that waves come from all directions. Basically what we have defined that 3D spectrum S, well, 3D omega is equal to S 2D omega, well, there is a theta here, multiplied by F theta. Like that we described. In other words, if you recall, what we have done is that we said that if we assume waves are coming from all directions in addition to all frequencies in one direction, then the spectrum that we get is a bell-shaped spectrum. In other words, the spectrum that will look like is something like, you know, coming, well, from all direction, and it will look like this. Then you have to draw here, then you have to draw here, you have to draw here, etc. It becomes a kind of a bell-shaped graph. In other words, let me put it this way: if you have drawn this, and if you rotate that this way, suppose there is a graph here, rotate that along with pulling it down, that would imply that you are actually simulating or representing an irregular waves where all the waves are coming from this direction plus this direction plus this direction plus this, etc. That means you are assuming that all the waves that are, you know, the wave height or elevation that you are getting is because of sum of all waves coming not only from one direction of all length but also from all directions, but the directional spreading gets sort of thinned down. In other words, there will be much larger waves coming this side, little smaller this side, little smaller this side, and ultimately no waves this side, and like that. And this was simulated by kind of multiplying this with a spreading function. So in essence what we are doing is that, see, that we are saying that there are waves coming, just give a 3 example. In one case I have all the waves coming from this side and it gives some energy, but in this case I will have all the waves coming from this side, but of course it will cannot have all the energy, so it will be maybe little smaller, you know, that if this is, and then there will be some waves coming from this side, some coming from this side, like that. Now what is happening now is, if this is the representation of spectrum, now if my ship is moving in such a wave, obviously I should have some mechanism to find out the response in such a wave, and this is more realistic because just think of it, a ship is moving and I am trying to find out you know, irregular waves coming all from the, you know, if you rather draw this way, all coming from beam waves. Now actually if all waves came from this side, then the ship would have rolled heavily. But if supposing in reality you will find that not all waves can ever come from one side, there will be quite some wave from one side, but there will be some from this side, some from this side, etc., etc. The waves are not normally all coming from one side, and if that happens, obviously it affects the response. For the clear case here, the roll, if you assumed all from one side, maybe it would roll say 30 degree, but if you assumed it is spread, then it will be probably less. Of course, from the design point of view, what we still do is that we take long crested wave, because if I have designed the shape to withstand roll for all waves coming from one side, obviously if it is spread, it will be less. So we are on a safer side. That is a different issue, but we should still know how we can calculate in short crested wave. Now the idea is very simple. See, short crested wave goes like this, that the principle goes very simple, that let us say I will just draw a case of waves coming from all sides. This is a wave direction, etc. Waves are coming from all sides, and for each side I have a spectrum. So I have S3D, or rather anyhow omega theta is given by S2D omega into f theta. F theta is a known function, therefore when theta equal to, for example, 0 degree, when I know that like f theta become 1, like that when theta becomes plus minus 90 degree, f theta becomes equal to 0, and in between that it goes. That means what you are multiplying the spectrum, see this is my wave direction here, what you are multiplying with that essentially is a, no, it's not 1, sorry, it will be some factor maybe 2 pi, I forget, some factor, so that when you sum them all up, actually the area under this and area under this becomes same. The theory, let us say it is known. What I am trying to say here is that we have a representation of short crested wave, okay, when we know how much of waves are coming from direction 1 and how much is from direction 2, how much from direction 3, how much from direction 4. Let us say you break it in say 10 degree interval. So you know all the waves coming from the dominant direction, if I call that to be say 0 degree, then all the waves coming from 10 degree, 20 degree, etc., etc. Now let us say on this the ship is moving in this direction. The ship heading is like this. Obviously what would happen is that it's very simple. Now I would know now all the waves coming from this direction to it. Then in other words, I know I know how much of waves come from this direction. So now, but all the waves of this direction makes an heading of so much.